In the last week, we have, or you have tried, no, not in last week, on Tuesday, you've tried to use Monte Carlo methods or the Monte Carlo first visit reinforcement learning approach to learn how to find an optimal lottery. So it's in a very, very simple setting. You wanted to find out what the optimal choice given a certain setup is. And we've seen that this led to sometimes useful results if we allow our algorithm to explore the state space to explore the state space completely, either by saying that the probability of exploring the state space is rather high, or by doing this whole algorithm for a very long time, so going over 100,000 iterations, for example, made sure that we had found the optimal policy in the end. When we come to more complex exercises and more complex situations, we had then seen that using Monte Carlo methods doesn't work anymore, because Monte Carlo methods required episodic tasks and we needed to finish the task at least once. And in this very simple toy example here, the task had never been finished because our cyclist here would have never made it through this maze without touching the black barriers or without getting out of the frame here, just by going randomly through the maze. So the idea then is that we need a class of algorithms or a set of algorithms that do not require us to finish an episode or even have an episode at all, but we could have one infinitely long episode that allow us, on the other hand, to learn in each step of the process. So not only after finishing an episode, but each period in time we do something, and after we did something we get a reward from that, and then we compare this reward to the value function that we have in the new state. So at least what we think the value function in the new state is, and compare that to the value function of the state we are coming from. So what we've seen basically is temporal difference learning, and it works in the way that we are in a state. Based on this state, we decide according to our policy to do something. Once we did that, we will observe a reward in the next period, and then we compare the future reward, so RT plus 1 here, plus the discounted, and the discount factor here might be 1 if we have an episodic task or a finite task. Of course, then we don't necessarily need to discount, but we can do that, of course. And we compare the future reward, the next day's reward, plus the future value function to our current value function, or to the value function of the current state. And this is what we have done in the last year in the dynamic programming context, as well when we looked at the Bellman equation, because this is just another way of representing the Bellman equation in the case that we have an actual realization of our next day's state. And we call this the temporal difference error, so the TD error, the difference between what we observe as reward plus next day's value function minus our current state's value function. And we can use this temporal difference error to learn something about the value function of the current state, because in expectation, and we see that on the next slide, the temporal difference error, given we are in a state, should be 0 if we have already learned everything about the value function. So if we knew the correct value function, then this expectation here should be 0, because then this right-hand side resembles exactly the Bellman equation. While we're learning the value function, of course, we do not have that in general, but we have that we either underestimate or overestimate, or we estimate not here in the sense of that we have a biased estimator, but in the sense that we haven't learned everything about the value function yet. We start at some values. We initialized the values in the exercise we've seen before with zeros. That obviously underestimated the true value function significantly, because of course the true value function has been always positive in this toy example of learning libraries. Meaning, if delta is larger than 0, that might mean two things. So this means that the value function of the state we are currently in is smaller than the reward we get from our policy plus the discounted value function of our future state. That means either v of the value function of our current state is too small, or the value function, of course, of our state in tomorrow is too large. As of today, we can't do anything about the value function of the state of tomorrow, so we stick with the value function of the state we are currently in is too small, so we need to increase that value function. So whenever delta is larger than 0, we also need to increase our current estimate or our current guess of the value function of the current state. And we do that with these update rules. So in the temporal difference case, we take this temporal difference error, multiply it with the learning rate parameter alpha, and add it to our current value function, to the value function of our current state, or our current guess or estimate of the value function of the current state. And this process, so this adding up small fractions of the temporal difference error to the current knowledge of our value function, converges if our alpha sequence fulfills these two conditions. So first condition, if we have an infinite long sequence of learning, then the sum of the alpha parameters needs to be infinite, meaning that we will never stop learning, but we'll always add a little fraction more to our knowledge of the value function. And the second condition is that the squared values of our alphas need to be finite, meaning that the rate we learn at decreases in such a way that we reach convergence and that what we know or what we think the value function is doesn't explode. Sometimes, or rather often, in general, you don't have infinitely many learning periods, of course, but only a finite number of learning periods. And sometimes for convergence, so it's not actual convergence, but in a way that it leads you to the right result, it is sufficient to have a constant yet very small rate alpha. Then you won't learn in the beginning very much, but in the end, the learning rate might fit. In the exercises you see in a couple of minutes, we will work with a learning rate that doesn't fulfill the second condition, I think, because the squared learning rates would not be smaller than infinity, but it ensures learning in a finite period of time, or in a finite time horizon of learning steps.
May I ask something? Sure. Just to make sure that I'm still on board.
Yeah.
So basically, if I were to rephrase what you are saying, I would say, this is what I have. This is my notion of this process. So you start out basically with an initial guess of the value function for every state. This is whatever your guess is, whatever that might be. Then you do something, then you get a reward and a potential new state due to the thing that you are doing.
Mm-hmm.
And then you use basically this updating rule. So you look at the reward and you look at the VST plus 1. So VST plus 1 is basically also an initial guess at the new. So this is the first step at the new state that you consider.
Yep.
Then you update the value function for the state that you are in, and then the next iteration starts.
Yep.
So this is the idea. Okay. Thank you.
Yep. And
one more question. If you go back to the example with the cyclist, the problem in the Monte Carlo case was that the cyclist would just choose any action randomly, and therefore the chance of really getting through the maze to the target area is just very, very small. It's so small that it never happened in these millions of times.
Yeah.
And the policy the cyclist had was just to choose any action randomly from the set of all actions. If that is the policy we would like to evaluate in the temporal difference approach, wouldn't we have the same problem?
We would have the same problem at the start, but if we assign a large negative value by either hitting the wall or getting out of the frame here, then every time we would leave the frame or we would hit a wall, we would have a large negative value here, and the policy would learn, or the cyclist would learn a policy that avoids these walls.
So the policy evolves during the learning process.
Yeah. The value function and the policy both at the same time evolve during the learning process.
Something. Or we have to change our potential set of actions.
Yep.
But that's not on the slides, isn't it? There's no...
Not on the slides yet, but on this slide it is.
All right, okay.
The slide I wanted to present next.
I'll wait.
Okay, this is the first temporal difference algorithm that you will be learning in this course. It's the SARSA algorithm, and SARSA stands for state, action, reward, state, action, as you can see in the plot on the bottom right. And the idea is that you start in a state, obviously, and in the first time you have to consider that you have already chosen an action. So be in the mindset that you have already chosen for an action, then you execute that action. The way you chose it before the algorithm start doesn't really matter. Then you execute that action. Of course, after executing that action, you will receive a reward, and you will be in a new state. And in that new state, you then choose an action. That's one iteration of the SARSA. After you chose that action, the next iteration of the algorithm starts again at a state. Then you execute the chosen action, you get some reward. The action brings you to a new state, and in this state you choose a new action. And then the next step of the algorithm starts in that state with the chosen action that is then just executed, which brings you to a new reward and a new state, in which you again choose for an action. That's the timing of the 5 steps of SARSA. And the idea let's just transform that to algorithmic notation. Before we start, we have, of course, to initialize everything. We have to set a step size parameter. We have to set a deviation parameter from the optimal policy. We need to initiate here the action value function, because that one later will help us to determine the policy. If we only had the value function, determining the policy would be a little bit trickier, because we had then to compute, again, the next day's value function and needed to derive from that
So just a quick question because I'm again a bit confused. So the Q and the V, this is not the same, right?
The Q is the V split it up in all possible actions, so to say. So if I do an action today, action A today, and after that I follow the policy. Besides that, they are identical. So the concept behind both is similar, but not exactly the same. V is, I am in a state and I always follow the policy. And Q is, I follow once action A and after that the policy.
So this is basically a contemporaneous deviation.
Yep, of the policy. And if we have an episodic task, we need to set the remaining value, of course, of any action, because there are no actions after the terminal state, to 0. So in the case of riding through the maze, the green finish line would receive a terminal value of 0. If we have a non-episodic case that runs for an infinite period, we don't, of course, need to set to be aware of this. Then if we don't have an episode, we can, of course, skip this outer loop. But if we have episodes, then in each episode we need to initialize a starting state, and we choose our action given our state already from the policy based on Q. In the very first iteration, of course, the policy based on Q, if we initialize Q with equal numbers, the policy is of course totally random, so we need to choose an action at random for the very first time, and then we go through each step of the episode, or to an infinite number of steps if we don't have episodes here. We take the action, so we execute the action. For example, choose lottery 7. Then we observe a reward, and we observe a future state. And from this future state, we choose another action based on our current knowledge of the policy, or based on our current policy. So the policy, of course, based on Q. And once we did that, we already know where we are in the future, because we know the future state, because that one has just realized. And we know what we are going to do in the next step, because we already chose the next action. So what we know is the current state action combination, or the current state action value. And we already know the future state action value. So because we already know the future state, and we already know what we are going to do in the future. And then we can use our temporal difference update. So the new action value function is equal to the old action value function plus the deviation of the old value function from the old value function at the new state and new action plus the reward we observe. And after we did that, we have to, so to say, set the old state to the new state and the old action to the new action, because then these will become A and S up here. And then we run this algorithm over and over again. And after some time, we might or we will see that this algorithm converges for both for the value function or the action value function, and will converge for the policy. So we will receive in the end the policy. What's actually missing in here, and I'm very sorry for that, is that we also need to update the policy. So we, in here, in the second line of the inner loop, you say that we choose the new action from A using a policy based on Q. This implicitly means we need a policy based on the current version of Q. So implicitly here in this line, it is stated that we need to update the policy. But explicitly, let me say that we need to update our policy after each update of the action value function. Of course, only for the action values, we only need to update the policy for this current state, because all the other states haven't changed. So we don't need to run a full update of the policy each time, but only for the policy, we only need to update the policy of the state we are currently in. So to update the probabilities of the states we are currently in, for the states we are currently in.
Maybe another ignorant question. Capital letter S and small case s is just the S is a number and the capital S is the vector?
Are there any?
line 2, it says Q
Yeah,
of
you're right.
lowercase s, lowercase a.
But
Or
that's
is it
just the
typo?
function definition. This is the function definition of two variables. It doesn't really
So
matter
this is a number, basically?
Pardon?
This is a number?
No, this is the function definition. These are the two variables, and these are the numbers. So this is a general function. Might have also said x and y here.
Okay.
And this S here is an actual number or an actual state. Doesn't necessarily need to be a number. Could also be n. Could also be whether it rains or not. Doesn't need to be a number.
What I'm still missing is the optimization. I mean, the title says that we are estimating the optimal Q function, so the optimal state value function, but there's no. So choosing a prime from the set of all actions means choosing the best action from A.
No.
Or using epsilon greedy policy, which almost is choosing the best action.
Yeah, that's what.
So not just using any policy. So
Right.
We could also choose a prime from calligraphic A just randomly, but this is not what we are doing here.
Right. We should have been more clearer here that we need to work on an epsilon soft or epsilon greedy policy here.
Mm-hmm.
So that is actually the maximizing step that was in the Bellman equation. The maximizing operator from the Bellman equation is translated in using an epsilon greedy policy and updating that epsilon greedy policy at every step. Yes.
Yeah, I think it's quite nice to see the Bellman equation here again in the line in the last, but
this line.
Yeah, this line here in the square brackets is more or less exactly the Bellman equation.
Yeah.
Or if we put everything on one side of the equation, so the value function in the current state is the Q of S and A, and if we put that on the other side, then that would equal the instantaneous utility R plus the discounted value in the next period. That's really very, very neat.
All right, are there any further questions on this algorithm?
I have a question.
Yeah.
Can you please explain the difference between the episode and the step? It's not clear to me to differentiate between both.
If we, for example, want to go back to just a second to this example here, an episode would be to go from here, from the green line to the red line the whole way. This would be one episode would look like, for example, this would be one episode of the game. One step, on the other hand, is to go from the start line by choosing the action accelerate in Y direction to go from the start line 1 unit up. That's one step of the game. Then we can decide again what to do, and we decide, okay, let's also accelerate in X and Y direction, and we go one step to the right, 2 steps up. That's the second step of the episode. And so on. So this game evolves over many steps until this episode is finished.
Okay, thank you.
And that's what's meant with this here. We run many episodes, so we need our agent to go through the maze lots of times until we finally learned a really optimal way. Obviously, our agent does not need to go up there many times. The agent doesn't need to go into the wall many times. Everything that is, let me have a go to this. Everything that is far away from the optimal path, we don't really need to encounter often. We don't want to look at all these points and don't want to optimize over all these points at every time. So we are going, with each episode, we should go less steps to finish this episode in here.
So when we initialize the state, so this is here the first line in the outer loop, we choose the actual starting state.
Yep.
Or one of the possible actual starting state. All right.
It might either be always
necessary. It's not necessary to, in the case of this cyclist, it's not necessary to place her, say, at position 95 or 82, 11 to start with. So we really choose one of the green points. One of the points
I chose one of the green points.
The green lines.
Yep.
Okay.
But maybe some in the sense of philosophical remark. When you, for example, think about an agent choosing his optimal consumption path using this, then the agent obviously only has one episode to play, right?
The agent, his or herself, yes. A hypothetical, you could also then think of episodes being that you have 1,000 hypothetical agents who are doing the same job, one after each other, and one learns from the first one. So one agent does this, plans his or her consumption path, everything turns out, and she goes to the second action, tells her what her idea was about the consumption path, how it turned out in reality, and then she can go and do the same for her life.
I got another question.
Yeah.
May you go back to this slide with the cyclist, please? So if I got it right, so one step is just one unit in one direction, right? And one episode is the cyclist goes from the from the green points to the red points, right? That is one episode. So, but if the cyclist doesn't make it, so he hits the one of the black bars, for example, when does the episode end? And is it an episode if he doesn't finish?
The episode...
Or what is this called? What is that called?
So in the case of going to crashing a black barrier in here, I just restarted so put her back to the start, and she could go on. So that is the reason why.
So it's the same episode then, or?
Yeah, it's the same episode. That's the reason why this iteration should mean episode. That's the reason why it took roughly 1 million steps in the first episode.
Okay, so
as you can see
within
here,
one episode you update the function.
Yep, within the episode.
Within, yes.
After each step. And as you can see in this graph, she hit the wall quite frequently.
Yeah. All right,
and then
thanks.
was reset.
So we are having many sarsas in one episode.
Many sarsa steps. The algorithm itself is called sarsa. So many of these sarsa steps within one episode, yes.
Okay.
I'm just curious, how did you define the reward? Is it like distance to the red area? Is that enough? Or did you have to define it specifically?
The reward was just 1 for each time step.
Mm-hmm.
And I think 500 or something for hitting the barrier. And then I not maximized the reward, but minimized the sum of the rewards.
Mm-hmm. Okay.
I think it was 1 for each time step. So I chose in the end the policy that had, of course, that the cyclist was as fast as possible.
Interesting, thank you.
Okay, luckily the exercise Jane's Car Rental is a non-episodic game, so you don't really need to bother with the episodes. The exercise is rather long. It starts rather gentle and it is inspired by an example of the Sutton book. So I think we will do this today and on Tuesday, at least, and on Tuesday. And just so you can get used to this SASA approach.